Now, in terms of form, there are two different types of waves. One is called transverse. The other is called longitudinal. Okay? Transverse waves are the classic waves that you think of when you think of a wave, right? They're the waves that look like the little squiggly. Okay? This is transverse. And what makes a transverse wave is that while the wave propagates in this direction, propagates means move, right? So the wave moves from here to here, right? The oscillations, the vibrations in the wave are up and down. Okay? So in other words, in a transverse wave, the vibrations or oscillations in the wave are perpendicular to the direction of propagation of the wave, right? So the energy is moving this way, but the wave itself is vibrating up and down. Okay? That defines a transverse wave, and I'm going to do the best I can to show you what it looks like with a slinky over here. There's only one of me. It's a very lonely place here at Cuyamaca right now, but I'm going to do the best that I can. Okay, so a transverse wave is one that looks like this, right? Propagates like this. Okay. In other words, even though this wave is being reflected from this hand back to this hand, back to this hand, back to this hand, right, the oscillations are up and down. All right, you get the idea. If that wasn't clear, which it probably wasn't clear, there are a million places where you can Google transverse and longitudinal waves and see. Okay, but longitudinal waves, what are they? Well, longitudinal waves are waves in which, and this is a little bit harder to draw, but they're waves in which is exactly the opposite of transverse. The vibrations in the wave are parallel or in the same direction as the propagation. Okay, so for example, the wave's going to be propagating in this direction, but the particles themselves that make up this wave are a compression, rarefaction, right? That means less density in terms of molecules. Compression, rarefaction, right? And so the vibrations, the jiggling is in this direction, right? And the propagation is also in this direction, okay? So for a longitudinal wave, the vibrations of the oscillations are in the same direction or are parallel to the motion of the wave. That's longitudinal. Okay? Now I'm going to try to do that with a slinky as well. Okay? It's going to be a little bit harder. Let's see if I can do it. Okay. So I'm going to bunch up a bunch of the slinky right here. Then I'm going to let it go. Okay. You could see it at least for the first part of it. I wish I could do this in slow motion, but you'll see that this little clumped up part right here starts to oscillate, reflects off this side, bounces back again. You see that? Right? So the wave is traveling in this direction, and the individual oscillations of the slinky pieces, right, these little slinky loops, are also in this direction. Now, one way that I can do this if I was going to do interpretive dance for what a transverse wave, it would be something like this. Transverse wave is like, right? If I were to do an interpretive dance of a longitudinal wave, it'd maybe be something more like this. Okay? I hope this is coming together to help you understand. And, you know, I don't mind making a fool of myself to create more understanding inside of your brain. That's the most important thing here. Okay, now, where do we see transverse waves and where do we see longitudinal waves in the real world? Well, transverse waves are electromagnetic waves. In fact, you can see this in the slide that I have here, right? There are electromagnetic waves. There are ocean waves. And there are shear seismic waves. So there's two different kinds of seismic waves. One of them is shear, and those would be longitudinal waves. Right? Transverse waves also tend to be the classic, wave on a string, like if you're doing a jump rope or something like that. Okay. How about longitudinal waves? Where do you see those? Well, let's go to that slide. Right. Longitudinal waves most commonly show up as sound waves. I'm almost out of breath here from all the interpretive wave dance. Okay. So you have sound waves. You also have basically any kind of pressure waves. Technically, sound waves are pressure waves. And you also have compressional seismic waves. So some seismic waves happen because the actual Earth, what composes the Earth is compressing this way, and some of seismic waves happen that what the Earth is made up is actually waving this way. Okay? So besides the fact that these look a little bit different and they behave a little bit differently, they're really all still made of the same stuff. This is still one full wavelength, right? And then from the beginning of a compressed part to a spread out part, that's still one full wavelength. They still both have a frequency. They both still follow the wave equation, V equals frequency times lambda. All other aspects of these two waves are identical. They're just built a little differently. Okay? All right. With that said, we will talk about what happens when either one of these waves meets another one of these waves. Okay? That's called interference, and we'll talk about it in the next video.